This is Steve Piloff from George Mason University. We're going to talk about growing perpetuities. Growing perpetuity, it's like a fixed perpetuity in the sense that it pays cash flow that takes place regularly, never ends, and makes its next payment in 1 year, in one period. So you got cash flow 1, cash flow 2, 3, and it goes forever and ever and ever. But what makes it a growing perpetuity is that the cash flow grows at a fixed rate. So here you have in one period your cash flow. What's the cash flow of the next period? It's simply equal to the previous one times 1 plus g. At time 3, the cash flow is the previous one, which was C2, times 1 plus g. At any point in time, the cash flow is simply the previous cash flow times 1 plus g. One of the ways to think about it is that there's an intern whose job, these are the amounts that are going on checks that an intern is going to send out at different points in time. And so all the intern has to do, well, time 1, that's kind of your starter point. It starts in one period. So you have your starter, and then at any particular point after that, all you do is say, what was the last dividend, what was the last cash flow? Multiply by 1 plus g to make this one g higher, and that's how you can figure it out. But if we know here, we know it's the previous one times 1 plus g, but we know this one is just c1 times 1 plus g. What we see is that the cash flow at time 3 is equal to this cash flow times 1 plus g squared, the cash flow at time 1 times 1 plus g squared. And you can think about it as there's some cash flow here. This one here is this times 1 plus g. Then you've got this one, which is c1 times 1 plus g, times 1 plus g is the cash flow that you get there. So at any point in time, the cash flow that we expect at that point in time is the one that we expect at time 1 times 1 plus g to the power of the number of times it grows from time 1 to time t, so it's t minus 1. So again, a lot of times if we're dealing with something at time t, people might say, well, it should be time t. You have to count. It's because we're starting here at time 1, and if you count the jumps, you'll see that there's t minus 1. So let's take a look at an example. We want to know what the cash flow is expected to be in 5 years. Investment pays investors every year forever. The next payment's expected in a year, and it's expected to be $1.40, and after that all subsequent payments are expected to grow by 5.5% per year. So what is C5? What's the cash flow we expect in 5 years? And the answer is $1.73.4. So here we have $1.40. 1 year later, the cash flow is $1.47.7 because the cash flow increased by 5.5%. If it increases by 5.5%, again, it's 147.7 times 1.055. So in 3 years from today, which is 2 years from 1 year from now, we expect the cash flow to be $1.55.8. A year later, $1.64.4. And then out here, in 5 years from today, or 4 years from here, we expect $1.73.4. You got $1.40, and it jumps 1, 2, 3, 4 times 1.055 to the fourth because it grows by 5.5% per year, and it'll be $1.73.4. So we've established already that the cash flow at any particular time is simply, and there's constant growth, is equal to the previous cash flow times 1 plus g. Or you can also view it as being equal to the cash flow at time 1 times 1 plus g to the t minus 1, because from time 1 to time t, there are t minus 1 jumps. So that leads us to the fact that if we know the cash flow at some point in time, and we want to know what the cash flow is at some other point in time, it's called a later point in time, so b is greater than a, then it's just whatever the cash flow is at time a times 1 plus g, which captures the growth. But for how many periods is it from a to b? It's just b minus a. So if this was time 3 and this was time 5, it would grow 5 minus 3, 2. So at time 3 you'd have that, time 4, time 5, it'd be whatever it is at time 3 times 1 plus g squared. And that's what you can see down here on the timeline, where you've got the cash flow at time 1, time 2, time 3, time 4. You can always express them in terms of the previous cash flow times 1 plus g. You can always express them in terms of the first cash flow times 1 plus g to the t minus 1. And here I just took, if we know that, this one's that times 1 plus g, that times 1 plus g squared. And so hopefully you get an idea of how, again, these are amounts on checks. The intern, if we know what the check was at a particular point in time, and we know the growth rate, then we can figure out what the amount on the check is at any other subsequent time. In fact, you could even figure out earlier as well. So by knowing this, that if we have one cash flow and a growth rate, we can find the expected cash flow at another point in time. We also know that if we have any two expected cash flows, we can find the growth rate. Again, we're assuming we're in a place where there's constant growth rate. So if we knew, what C2 was and we knew what C8 was, we could figure out what the growth rate is to get us from C2 to C8. Therefore, if you have any two expected cash flows, you can find the expected cash flow at some other point in time, because you can use A and B, the cash flows at 2 points in time, to say what's the growth rate that if it started here and ended here and it had this many periods, it would have to grow that amount per period. And if you know that, then you know what it would grow from there on ever, and you know what it would have grown in the past, if the past is relevant, but certainly the future is. So let's take a look at an example. We want to know what the cash flow for investments is expected to be in 4 years. So this is what we're trying to find. Investment pays investors every year forever. So every year forever sounds like it might be an annual annuity. Annual perpetuity. The next payment is expected in 1 year, so that's good. Payments are expected to grow at a fixed annual rate forever, so now I know we're dealing with growing. What do we know? We know the expected cash flow in 3 years is 212, and the expected cash flow in 6 years is 238. So we know this one, and we want to know this one. But what we know will lead us to our approach. Number one, find G. We know that C3 times 1 plus g to the first, to the second, to the third, C3 times 1 plus g times 1 plus g plus 1 plus g is equal to C6. That we want to find the growth rate such that if we started with 212 and it grew 1, 2, 3 periods, it would be equal to, or it would be, the check would be 238. So what's the growth rate such that 212 times 1 plus g times 1 plus g times 1 plus g, or 212 times 1 plus g to the third, is equal to 238. Then once we have the g, we can figure out what the expected cash flow is going to be in 2 years, because we know this, it's going to grow by 1. And if we knew this, what we know is that this cash flow will grow by 1 plus g squared. Or if we knew what this is, the cash flow here at time 6 would be this times 1 plus g squared, and that's 238. So 212, intern shows up and says, oh, it was 212 a year ago, what should it be this year? 212 times 1 plus the growth rate. Or, since we know that this is 238, and we knew it grew at the growth rate, or the size of the cash flow grew and increased, this times 1 plus g squared is equal to this. So let's figure some of it out. Again, we know that we went from 212 to 238 in 3 periods. What's the growth rate? Remember that if you take both sides to the 1 over n, the coefficient here cancels out. So, if you have 6 to the third, actually 6 to the fifth, to the power of 1/5, that's simply equal to 6 to the first, which is equal to 6. So if you take something to the power of 1 over that, the product's equal to 1. So you can basically get rid of that. do we do down there? So 1 plus g is equal to 238 divided by 212 to the 1/3 power. Put that in your calculator, and you'll see that it's 3.93. That 212 grows by 3.93% till 4 years from now, to 5 years from now, and from 6 years from now. So we know that 212 times 1.0393 to the third gets us to 238. So what we want to know is, okay, if we're at 212 and it grows by 3.93%, so that times 1.0393 is equal to what we're trying to find. Or what we're trying to find times 1.0393 squared is equal to 238. And we can see that either approach leads us to the mystery cash flow being $2.20 and 0.3 cents.